Recording in progress.
Very good. So today's CADNOF seminar is being given by Sridip Pal from the IAS, and he'll be telling us about automorphic spectra and the conformal bootstrap.
Thank you very much for the invitation. So today I'll be talking about the automorphic spectra and the conformal bootstrap. The talk will be based on this work done in collaboration with Peter Kravchuk and Mazac. So as we all know, we are more or less familiar with the idea of conformal bootstrap. So in the conformal bootstrap, we generally talk about CFTs. We take 4-point function and we impose the crossing symmetry to put constraint on the CFT data. For example, we put bounds on the operator spectrum of a CFT, we put bounds on the OP coefficients and so on. So today our goal would be to show that the same kind of ideas that appears in conformal bootstrap also appears in a distant land, which is the realm of automorphic spectra, and we can use similar sort of ideas like crossing symmetry, associativity to put constraint on the automorphic spectra. So to begin with, what do we mean by automorphic spectra? So automorphic spectra is, you can think of them as a generalization of periodic function defined on some group manifold. And here, as you can guess, the group manifold or its quotient. So here, as you can guess, the relevant group manifold would be the conformal group manifold. And also another important player of the game would be a quotient of the conformal group manifold, which is called hyperbolic manifold. So we will see that given any hyperbolic manifold, one can define notions of operators. We can define notions of operator product expansion, and which will follow some associativity. And as a result, we can define some crossing symmetry given some hyperbolic manifold. And then using the same sort of ideas that appears in Bootstrap, we will use those ideas to use the crossing symmetry that appears for the hyperbolic manifold to put bounds on the automorphic spectra, in particular the Laplacian spectra on a hyperbolic manifold. So roughly that will be our goal. Our goal would be to understand this connection between the conformal bootstrap and the hyperbolic manifold, and to see how the same ideas appear in the case of hyperbolic manifold, and to see how hyperbolic manifold gives us a toy model for a CFT. And as an output, as a byproduct of all these things, we will prove some nice results about Laplacian spectrum on a hyperbolic manifold. So that will be our goal today. So to start with, we can so as I was saying, so we have these two diamonds here. On the one side, we have the conformal bootstrap in D-1 dimension. And on the other side, we have the spectral geometry of a D-dimensional hyperbolic manifold. And our objective is to show the remarkably precise connection between these two things, which is made possible by this group SO1, D. And this 0 means here we are looking at the connected component of SO1, D. On this side, this appears as a space-time symmetry. On this side, this appears as a orientation-preserving isometric group of this hyperbolic manifold. So in both cases, the key role will be played by some representation theory involving SO1, D. And as we go along, this connection will become more and more clear.
The 1, D will be important as opposed to D+1 or 2, D-1.
Yeah. So there is a one subtle difference. So here the key roles will be played by the unitary representation of Euclidean conformal group. But in the usual conformal field theory, the key role is played by the unitary representation of the Lorentzian conformal group. So there is a slight difference. But if you forget about that fact, then the other structures are same. There is a notion of OPs, and they furnish a representation of SO1, D. You can define operator product expansion. They follow some associativity and so on.
Is the index 0 in SO0?
Oh, the 0 refers to the connected component of SO1, D. That's it. And this basically means on this side we are looking at the orientation preserving isometry. Yeah. Good. So to move ahead, why doesn't it work? So my keypad is not working. Anyway, so the next question is, why do we care about this problem? Now the answer depends on exactly from which background you are coming from and exactly what you are looking for. So from a physics perspective, that, as I was emphasizing, that it provides a nice toy model for a CFT. So you can ask various questions which is otherwise very hard to ask in actual CFT setup. For example, it is very hard to bootstrap a chaotic CFT, so you can ask these questions that can crossing provide us a solution which exhibit chaotic features. So because the spectral geometry of hyperbolic manifold provides us a toy model, you can ask the same questions about various hyperbolic surfaces. For example, there are non-arithmetic surface, 2D surfaces, hyperbolic surfaces, where it is numerically known that the spectrum of the Laplacian is actually chaotic and show RMT-like features. So the idea is, if we can bootstrap those surfaces, if we can figure out some extremal functionals that gives out the spectra of those spectra of the Laplacian on those surfaces, we can actually furnish a case where the crossing provides a solution which exhibit chaotic features. So that's one sort of physics motivation, like because it's a nice toy model for CFT, we can ask various analytic questions, which is otherwise probably much harder to ask in the context of actual CFT. And from the math, is there a question?
Yeah. Is there a relation between what you're about to do and the Selberg trace formula, which basically relates hyperbolic geodesics to spectrum of the Laplacian and therefore chaos and so on?
Yeah, so the thing is, no, there is no direct relation, but you can also set up a bootstrap problem, which will be a separate bootstrap problem to bootstrap the Selberg trace formula. And that will give you some information about some bounds on geodesics, so if you set up a bootstrap problem involving Selberg trace formula, this will give you some information involving the lower bound on a length of closed geodesics, some upper bound on Laplacian spectra and the area and so on. So it is possible to set up a bootstrap problem, but that bootstrap problem is separate from what I'm going to tell you.
Okay.
Because here in the thing I am going to tell you there, like we will not be using any information about the geodesics. But while on the other hand, in the Selberg trace formula on the right hand side, you have the closed geodesics and so on. And okay, to move ahead, so there are also motivation from the math literature. For example, there are unproven conjectures in math literature. For example, like there's a conjecture that among all genus 2 surfaces, there is a spatial surface called Bolza surface, which maximizes the gap in the Laplacian spectrum. In the same way, in the genus 3, the conjecture is that there is a surface called Klein quartic, which maximizes the Laplacian gap. And to prove this kind of conjecture, bootstrap is a nice handle because bootstrap always gives you an upper bound. And once you have an upper bound, you can always check your upper bound with the actual numerical value on those surfaces, for example, Bolza and Klein quartic, and you can actually hope to prove these unproven conjectures in the math literature. And also furthermore, you can ask various structural questions about how the spectrum of Laplacian looks like in general as you scan over various hyperbolic manifolds. So you can answer those or try to guess those structural questions using the bootstrap kind of approach. And finally, we have this, as I was saying, that SO1, D will play a key role. So there could be a possible connection with the D-sitter bootstrap, which has been initiated by these people recently. And there also the crossing equations they write down actually based on SO1, D. And there also the unitary, the representations that appear there are unitary representations of SO1, D. So in principle, there is a mathematical connection with the D-sitter bootstrap also. So these are roughly our motivation. And with this motivation, we will go ahead.
So when you say maximizing the Laplacian gap, is that at some fixed value of something, or?
It will be clear in the next slide. Just hold on a moment, and you can ask me the question again. So. Okay. Sorry. Yeah. So for the rest of the talk, I will be, so in general, the thing I mentioned can be done for any d-dimensional hyperbolic manifold. But for the rest of the talk, I will be focusing on 2-dimensional hyperbolic manifold, which is the simplest of all and has rich structure. So how do you think about these 2-dimensional hyperbolic manifolds? And in particular, I will be looking at a compact hyperbolic surfaces. So the way to construct them is to consider the upper half plane H, and then realize like if you endow H with a upper half plane metric, the hyperbolic metric, then the orientation preserving isometric group of this upper half plane is the PSL2R. Then you consider some discrete subgroup of PSL2R, which is called Fuchsian group, and you quotient the upper half plane by this Fuchsian group. And this gives you a hyperbolic surface. And then you want a compact hyperbolic surface. To do that, you ensure that your gamma doesn't have any parabolic element. So in principle, like all elements of PSL2R can be classified into three parts. One that are conjugate to rotation, they are called elliptic. One conjugate to scaling, they are called hyperbolic. And one conjugate to translation, they are called parabolic. So as long as your discrete subgroup doesn't have any element which is conjugate to translation, that is, doesn't have any parabolic element, your surface is guaranteed to be compact. And if your gamma has elliptic element, then your surface is orbifold. And if the gamma doesn't have an elliptic element, has only hyperbolic elements, then your surface is a smooth surface, it's a manifold. In this talk, the manifold and the orbifold are treated on the same footing. It doesn't really matter as long as the surface is compact. And it will become clear why we want a compact surface in the next slide. So how do you define the Laplacian on this hyperbolic surface? So on the upper half plane, the Laplacian is defined by this operator, which comes from the metric. Then we know our compact hyperbolic surface is the upper half plane quotiented out by this gamma. So basically, when we solve the Laplacian on these compact surfaces, we are basically looking for eigenvalues corresponding to gamma invariant eigenfunctions of Laplacian. So you solve this equation and you only pick those f's such that the f's are invariant under this Fuchsian group gamma. And because our surface is compact, that means the Laplacian spectrum is discrete, and this is why we want the compactness. Because if we have a compact surface, then the spectrum is discrete, and then it makes sense to put bounds on these quantities. So the first of all, because the surface is compact, it also has a finite volume. So the lowest eigenvalue is 0, which is a constant eigenfunction, which solves this equation with lambda I being 0. And then there is a gap, and then there is a lambda 1. So here our concrete goal is to put a bound on this quantity lambda 1. And in all these cases, whenever, in all these cases, the Ricci scalar is fixed to -1. So that's the convention we are using. So with this convention, the lambda 1, we will prove some bounds, numerical bounds on lambda 1s, which are rigorous. So is the goal clear?
Any reason why? So is lambda 1 the only one accessible with this method, or?
Oh no, so the thing is, like, you can also put bounds on lambda 2, lambda 3, like you have to enlarge your search space and do a bigger bootstrap problem.
You mentioned seeing RMT, so there you would probably want to.
Yeah. So there, my statement was in this way that you can put a rigorous bound on lambda 1, and then from the SDVP you can get the extremal functional and plot the extremal functional, and there will be some dips, and the dips very much will approximate the higher eigenvalues. I'm not sure whether I skipped a slide. No, my computer is somehow not. So the first question is, why do we expect a bound? And so like the whole talk is about answering this question, why is there a bound? But roughly speaking, like Hinterbichler and Bonifacio showed that, like, you can define functions on the manifold and you can multiply those functions, and these functional pointwise functional multiplication on the manifold, they are associative. So there is some notion of associativity in the functional multiplication, and that precisely gives you some sort of crossing symmetry and some sort of crossing equations and so on. But in this picture, there is no notion of groups, no notion of conformal field theory, and so on. So our idea is to recast this whole problem in the modern incarnation of conformal bootstrap, where we have a 4-point function. So at the end of the day, our goal would be to, given a hyperbolic manifold, we will write down some 4-point correlator, and we will study this 4-point correlator. We will define this notion of OPs, we will write down some equation of this sort, and then we will put bounds using this kind of equations in the usual way. And by usual way, I mean by the way we are used to do in the actual conformal field theory. Okay, so first give you the results, what we can do with this. So these are one of the main results we can prove among many other things. So for example, we can prove that any hyperbolic orbifold, it can be anything, must satisfy this universal bound that lambda1 is less than 44.8883537. You can make the bound more specific, more refined. For example, you can ask what is the bound for all the genus 2 surfaces, and you can show that for any hyperbolic orbifold of genus 2. And when I say orbifold, I also include manifolds. So it's everything. So any hyperbolic orbifold / manifold of genus 2 must satisfy this bound, which is 3.8388976,481. And then any hyperbolic orbifold of genus 3 must satisfy this bound, which is 2.6784823893, and so on. So given these bounds, if first you ask what are the best known previous bounds from the math literature, it turns out for genus 2, the best known bound was from 1918 by Yang and Yao, and the bound was 4. So we did improve this bound from 4 to 3.83, which is quite an improvement. And for genus 3, the best known bound previously was by Ross in 2020, who improved the Yang-Yao bound for genus 3 and able to prove this bound 2.7085. But our bootstrap bound is also better than Ross, which is we have 2.67 something. So in some sense, these bounds are the best known bounds in the literature right now. And then you can ask how, whether these bounds are nearly saturating or not, how close we are in pinpointing some actual surface. And again, it turns out we are actually quite close. For example, there is a surface, there is an orbifold which has the smallest volume, which is known in the math literature, which is basically a 3-punctured sphere with some particular orbifold ordering. And you can solve the Laplacian numerically on that particular surface. And it turns out that if you numerically compute the Laplacian thing, then it actually matches with 44.883537 in all the digits. In the same way, you can compute people have computed the Laplacian on the Bolza surface, which is a genus 2 surface. And there the value obtained numerically is 3.8388887258. And you can see that our bound matches with this value up to 4 decimal places, and our bound is slightly bigger than this, as it should, because this is an upper bound. And the hope is, as you put more and more equations, so in principle you have infinite number of equations, we only use a finite set of them on the computer, and in principle the hope is if you use more and more equations, these two values will converge with each other. And in the same way, in the Klein quartic, you can see the known value from the literature is 2.6779, and our upper bound is 2.6784. So again, this is quite close to saturating. So in all cases, it shows that our bounds are very nearly saturating. Maybe using more equations and mixed correlators and so on, we can actually prove these conjectures and show that the Bolza and Klein, they are really saturates the bound, and they are really the surface that maximizes the gap. Okay. Is there any question?
You have a genus n bound for the...
Yes, we have done up to genus 20. So I will show you a table later. And we also have a result for genus infinity, but it turns out that as we crank up the genus with fixed number of equations, the bounds become weaker and weaker. So for example, the mass folks still beats us in the genus infinity bound. They have a much better bound in genus going to infinity limit than us.
Sorry. And these are for Einstein metrics on these spaces?
Yeah, these are the hyperbolic manifolds with constant curvature. It's a sectional curvature fixed at -1. Right. So let us give you some examples of this hyperbolic surface, just to give you some flavor and set up some terminologies that we will use later. So the first kind of hyperbolic surfaces are like hyperbolic surface with genus 0 hyperbolic surface with 3 punctures. And the way to construct them is to consider these two groups called triangle group and the Bondi group. So basically what you do, you know in the upper half plane, all the geodesics are semicircles which cuts the real line on 90 degrees. So I made a mistake here, it should cut the axis at 90 degrees. But anyways, you get the picture. And then you have these three geodesics, and if they cut each other like this, you can form this triangle with ABC with angles alpha, beta, gamma. And if you can arrange for a situation where this alpha, beta, gamma is some pi over some integer, and then you can consider reflection around these three geodesics, and it forms a triangle group. But then the triangle group is a reflection group, so it changes the orientation. So you want to preserve the orientation. So to do that, you consider like pairs of reflection, which is and thereby you form a Bondi group, which is basically a orientation preserving index 2 subgroup sitting inside the triangle group. So if you are bothered about the like very mathy language, just remember you are basically considering pair of reflection so that the actual group is orientation preserving. And then the idea is if you take the Bondi group and take the upper half plane, quotient it by this Bondi group, you get a structure where you have a hyperbolic surface or a sphere with three punctures with a hyperbolic metric, and the orbifold order of these three punctures are given by these numbers k1, k2, and k3, which appears here. So basically, this if you take a Bondi group and if you quotient by gamma, then the upper half plane by gamma, then you consider a surface which has something called a signature, and you denote the signature by this element, which the first entry tells you the genus, so it's a genus 0 surface. And then there are a list of integers, which is k1, k2, k3, which tells you the number of orbifold points. Here it is 3. And this k1, k2, k3 denotes the order of the orbifold points, which is basically related to these angles. So I was mentioning about orbifold with smallest volume, and people have shown that the orbifold with smallest volume has signature 0, 2, 3, 7. In the same way, you can show the second smallest one corresponds to 0, 2, 3, 8. And here there is an important remark that oftentimes, it might give you an impression that if I tell you this signature, I am telling you everything about the surface, but that might not be true because the surface can have moduli. For the surfaces with genus 0 and 3 punctures, there is no moduli. So if I tell you 0, 2, 3, 7, I am telling you everything about the surface. But oftentimes surfaces are moduli, then you need to give in more information on top of this information. So this information in some sense is a topological information. And this will come so the takeaway from the slide is this notion of signature of gamma. And this notion will play a key role because later we will put bounds, genus specific bounds, and the information about genus or topology will come through this gamma. And I should also mention about the Bolza surface and the Klein quartic. So the Bolza surface has this nice picture. So this picture is taken from Wikipedia. So basically you take these 2, 3, 8 triangles and glue them properly, the 96 of them, and glue them properly so that you have this big surface with this identification 4 with 4, 3 with 3, 2 with 2, 1 with 1. And that's the most symmetric genus 2 surface. And the claim is that this maximizes the Laplacian gap. And in the same way, you can consider the Klein quartic, which is the most symmetric genus 3 surfaces, and which is basically a 14 gon and with some proper identification, and you can construct it by gluing these 336 of 237 triangles. So in most of our story, that the bounds we produce are actually saturated either by 237 triangle or 238 triangles, or by this Bolza or Klein, which can be made out of this 237 and 238 triangles. So in some sense, they have some nice spectra and they are amenable to bootstrap. So is there any question at this point?
So your bounds are constant over the moduli space?
Yes, our bounds are constant over moduli space. So that's why I was saying that the signature of gamma, that doesn't have any information about the moduli. It tells you about the topological type. And our bounds are only sensitive to the gamma. So if you change gamma, our bounds change. So in that sense, our bounds are not sensitive to moduli. So when I say I am producing a bound on genus 2 surface, that bound is applicable all over the genus 2. And just to, so as you will see later, there will be OP coefficients. So so in the bootstrap case, when you write down the crossing equation, there will be OP coefficient squares appearing everywhere in the crossing equations. And normally we take it, so generally the only input the bootstrap SDBP has is that the OP coefficient square is a positive number. And that's where actually the moduli dependence is hidden. Like if you want to make this whole program moduli dependent, then you have to put in information through the OP coefficient somehow. But we do not do that for our purpose. Good. Okay. So now we go back to our original problem, like how to make the connection between how do we bootstrap the hyperbolic surface, how do you construct operators, how do you construct Hilbert space, and so on. So the first thing one might think of when considering this kind of problem is to consider how do you construct a Hilbert space. We consider the functions that can live in the surface. So our surface is given by this upper half plane quotiented out by gamma, which is a Fuchsian group. So first you consider all square integral functions living on the surface. Of course, these forms a Hilbert space. They are nice. They are square integrable and so on. But then the problem is that this doesn't furnish a representation of PSL2R, which is the orientation preserving subgroup of the hyperbolic surface. So you want to construct a Hilbert space which is a nice representation of PSL2R. So somehow we have to enlarge this V0. So in the next step we will do that. So to do that, we realize the following thing, that this upper half plane H can be written down as a right quotient of G/K, where G is PSL2R, the group manifold, and K is the maximal compact orientation preserving subgroup of PSL2R, which is SO2, R slashed out by plus minus identity. So once you realize that H can be written down as G mod K, you can forget about the K and construct auxiliary Hilbert space, which is defined over G/gamma. So where you take the full PSL2R and then slash out, quotient out by Fuchsian group gamma from the left. And you consider all square integral function that lives on this bigger surface. So this is a 2D surface, but here this becomes a 3D surface now, because now basically we are appending an extra direction by removing this K. And this will be our new Hilbert space, which is L2 of G/gamma. And pictorially what is happening is following. So this X is our original space, which is G/H/gamma. And then on top of it, on each point, you are appending this S1, which is the K. And this whole space is G/gamma, and you are defining functions on this whole space, which is parameterized by x, y, and theta. And this f, x, y, comma, theta lives on this L2 of gamma, G/gamma. So originally we only have the surface and on functions living on the surface, but now we enlarge our space. We have this extra direction, which is the theta direction. And we are considering functions which lives on this bigger space. And the reason behind doing this is that now, as you will see, that this functional space actually forms a representation of PSL2R. Yes?
Should I just think of this as the trivial S1 bundle over X, or is there some extra content?
So it is trivial when you are considering when there is no gamma, but when you are quotient out by gamma, it's not trivial. But it doesn't really matter for us, because at the end of the day, the Hilbert space is constructed is L2 of G/gamma. So we are only considering gamma invariant functions. So you can still define, even if it's not trivial, you can define this Hilbert space. Okay. Please feel free to ask any question, because otherwise I might go very fast and you might lose the juice. Okay. So now we want to turn this Hilbert space into a representation space. So we do that by the usual way. We define an inner product, which is basically take two functions, complex conjugate one of them, and integrate over the manifold. It's a compact manifold. So, and these are the square integral functions. So this integral is finite and positive. So everything works out. It's positive when F1, like F2 is F1. And then how do you show that this is a representation of G of the PSL2R? That's also easy because this is a function which is defined on the group manifold itself. So there is a natural regular representation, which is basically you take a G tilde, act on a function F. This gives you another function, which is the original function evaluated at G tilde. And you can clearly check that this is a representation. So once you have this representation, the next thing as a physicist you do, you complexify the group, you complexify the algebra, you write down the generators, and you ask how the generators act on this F. Here the relevant group is PSL2R. So the generators, there are three generators, L1, L0, and L-1, which are all familiar with from 2D CFT or 1D CFT. So the next question, you can write down how this L1, L-1, and L0, these three generators acts on this Hilbert space. So I will give you the slide. So here you can see these are the explicit differential operators that acts on this function. L1 acts like this, L-1 acts like this, and L0 is I del theta, which basically picks up the charge under this rotation around the circle you just append over your actual 2D surface. And then note down the Casimir. The Casimir, if you write down the Casimir, then you see that there is a y square del x square plus del y square, plus there is some cross term. And if you're careful enough, like this gives you some hint that it might be related to the Laplacian, because if you forget about this piece, then you will see that the first piece that appears is precisely Laplacian. So this first tells you that there's a chance if I can say something about the Casimir, if I can put some bound on the Casimir, I might be able to tell you something about the Laplacian eigenvalues. And this is precisely what will be done. So now we will define correlators of functions on this space. And the correlators is defined in a very natural way. You take the functions, you pointwise multiply them on this group manifold, and basically integrate over G slash gamma. Again, everything is square integrable and it's a compact manifold. So this integral is well defined and gives you a number. Okay. Now I will make some important observations to actually connect it back to the problem on the surface. So first you observe that if your function f is theta independent, then this reduces to the earlier definition of correlators of functions. For example, like if all your functions are theta independent, then you can do the integral over this extra direction and rewrite this as an integral over the surface. So basically you can translate it to a correlator defined on the surface. So that's one observation. And another observation is that if you take the Casimir and act on some function which is theta independent, then this term actually drops out and you precisely get grad square on Laplacian acted on this function little f. But the little f is defined as capital F, but as a different function living on the surface. So the point of this slide is to show you that in this bigger Hilbert space, there is a subsector on which if the Casimir acts, gives you the Laplacian eigenvalue. So basically at the end of the day, we want to focus on this subsector and we want to extract some information. So now you can ask about what happens to the other subsectors, because in the previous slide I only told you about the functions which are theta independent, but then there are also functions which are theta dependent on living inside this V. So it turns out these Vn's are basically related to n forms living on the surface. And note, by doing this, we are naturally incorporating objects like covariant derivatives acting on eigenfunctions. So if you forget about everything, the main gist of the story is that earlier you only had functions living on the surface. But then the point is, on the surface there are forms, there are like derivatives of eigenfunctions, everything lives on the surface. And if you consider this bigger Hilbert space, all those forms becomes an actual function on this bigger space. So it's nicer to deal with this bigger Hilbert space. And then you can prove finite things inside this Vn, as I will do next. So you can ask whether there are spatial functions living inside this Vn so that they are annihilated by L1 or L minus 1. It turns out indeed there are some sectors living inside this Vn which actually annihilated by L1 or L minus 1. And so this F lives on the bigger Hilbert space. If you translate it down to the actual surface, then it will turn out to be the holomorphic differential or the anti-holomorphic differential living on the surface. So basically we are building a dictionary between something living on the surface and something living on the bigger Hilbert space. So once we understand all these subsectors, we ask the question we always ask as a representation theorist, which is following. Like, given this L2 G slash gamma, can we decompose V into irreps of PSL2R? And then the irreps of PSL2R comes in different kinds. The first one is the trivial representation, which is basically the unique identity in the language of CFT. And in the language of surface, this is basically a constant function which gives you the zero eigenvalue. And there is a only unique constant eigenfunction, which is like the unique vacuum in the CFT. Then you have this dn and dn bar, which is basically defined. So these are again irreps, and they are defined by these conditions that they are either their lowest weight and the highest weight representation. They are either annihilated by L1 or L minus 1. And you know that they are, like in the previous slide, I told you that they are related to the holomorphic differential and the anti-holomorphic differential. And the idea is, if I know the topological type gamma, then I can use the Riemann-Roch theorem on this surface, and I can exactly tell you the multiplicity of some holomorphic differential or anti-holomorphic differential of some particular weight. So the point is that not only I know that this appears, if I know gamma, I also know how many of holomorphic differentials of weight n and how many of anti-holomorphic differential of weight n appears in this decomposition. So we know this part, we know this part, and then finally we are left with this C lambda k, which is the continuous representation, and they are labeled by this lambda k, which is the Casimir of this representation. So here we have a lowest weight and highest weight, and in this sector we do not have a lowest weight and highest weight. It goes like above and below for infinity, and all of the states are labeled by this lambda k. And previously I told you that this Casimir is related to the Laplacian eigenvalue. So the whole point is, if I know, given a gamma, what kind of lambda k appears in this final sector, I can also know what kind of Laplacian eigenvalue appears for this surface, H slash gamma. So our goal is to bound or find out some information about the possible lambda k that appear in this decomposition. So that's our representation theory goal. And from that goal, we will tell something about the Laplacian eigenvalue and the Laplacian eigenfunction. Is there any question? Because I have packed too many things on this slide, I guess, but yeah. Okay, good.
Could you explain again how you see that the Casimir has to be the same as the Laplacian eigenvalue?
Yeah, so that's I explained here. So the Casimir is given by this operator here, and then the F, so on the last sector where C lambda k, there is no upper limit on n, lower limit on n. So there is a zero sector, and the zero sector is theta independent. And then this goes away, this part, and then it precisely becomes a Laplacian.
Okay.
And because it's a Casimir, it doesn't really matter exactly on which state you evaluate. It's the invariant on the representation.
Yeah.
So once you know something about C lambda k, you know something about the Laplacian. So now comes the crossing symmetry. So crossing symmetry is basically now becomes associativity of function multiplication on this bigger Hilbert space G slash gamma. And roughly the intuition is that this G slash gamma is something somewhat like configuration space. So if you change the G/gamma, you change the surface. And it's almost like you are dealing with a different CFT with a different spectrum and so on. So in actual CFT, the configuration space is of course infinite dimensional, but here we have a toy model of a CFT where you have all the structures of CFT and where the configuration space is a finite dimensional space given by G/gamma. So that's a rough analogy to have in mind. Okay, now we construct the operators. So recall in the CFT, how do you define operators? We insert in the radial quantization, we insert the operator at the origin, and then we translate it by L-1 and so on. So here also we do the same thing. We take the lowest weight state, which is denoted by Fna. So A labels some internal degree of freedom, and N labels the scaling dimension. So basically the eigenvalue under L0. So this is the lowest weight state. And you can act with this exponential operator, which is exponential ZL-1, which translates the analogous transformation is translating an primary operator from 0 to some particular point Z. So you have this operator ONA of Z. In the same way, you can take the highest weight state, which is denoted by F star NA, and you can do this operation to define some anti-holomorphic operators. And you can also define operators inserted on infinity with the usual prescription, like you take the operator Z and multiply with Z to the power 2n and take Z to infinity. And once you define these operators, the action of L1, L-1, and L0 of these generators on these operators are exactly same as if they are acting on some CFT operator with scaling dimension n. So now you start to see the CFT connection once you construct these operators. And as a word of caution, that this variable Z is an auxiliary variable, has nothing to do with the actual surface. So this is an auxiliary space you are constructing to construct your operators. So this Z is like the actual space time of the CFT. So next, once you construct the operators, you try to write down the correlators. So the 2-point correlator of two holomorphic guys is 0 because there is no identity. If you take a holomorphic and the anti-holomorphic guy, there is a identity in the OP channel, and the Z1, Z2 dependence is completely fixed by the conformal symmetry, like the usual way, the 2-point correlator. So you can write down the 2-point correlator. In the same way, you can write down the 3-point correlator, which comes with the usual functional dependence of the usual CFT, and then there is OP coefficients. So at the end of the day, what we learned, that either we can think of these 3-point coefficients in 3 different ways. For example, if we want to construct F2n, A, these OP coefficients can be thought of as a 3-point coefficients when you fuse this ON, and O2n bar, these 3 operators. Or you can also view them as something coming from this bigger Hilbert space where you take 3 functions and multiply them pointwise and integrate over the manifold. Or this same number can be produced by considering holomorphic and anti-holomorphic forms of weight n and weight 2n, multiply them together with some weight factor and integrate over the surface. So all these 3 gives you the same number. And originally we started our life, these things started their life from the surface, but now once we construct the operators, we can all forget about these things and we can play the usual CFT game. Like you start with these operators, you set up a 4-point correlator, you can try to bootstrap.
But how do you think of, this crossing in the language of integral over d mu f is pretty obvious, right? It's just, you're just saying.
Yeah.
In that language, how would you write down the decomposition in terms of 3-point functions? So let's say I write a 4-point function.
Yes.
In the language of integral over d mu with 4 f's.
Yeah.
And how would you decompose that into 2 different channels?
Oh, you basically take 2, so it's like you have F1, F2, F3, F4.
Yeah.
So either you can fuse F1 and F2,
yeah,
write it down in the complete basis, and F3, F4 write down in a complete basis, or you can do F1, F3, F2, F4. You see?
Yeah, so there's a resolution of the identity in the language of the f's. Did you write it down at some point? Or?
No, I'm not gonna write it down because I have translated everything in terms of this language. So that's the
this language,
but in principle you can also do it. But again,
Okay.
the problem of doing that in this language, it will be very cumbersome.
Yeah.
And you will also lose. So here, when you write down the 4-point function, you have all the information of blocks and everything.
Right.
But here, the information about blocks and everything is all like somehow hidden.
Yeah.
And it would be more cumbersome to actually write down something. But in principle, of course, you should be able to write down. Okay, so if you forget about everything, so here is a snippet. So basically we construct operators labeled by points on the Riemann sphere. They come in 3 kinds. So I told you there are holomorphic and anti-holomorphic differential. Corresponding to holomorphic and anti-holomorphic differential, you construct operators that live on the lower hemisphere and the upper hemisphere. So these are the ones I just constructed before, these OM and ON bars. And then there are operators that live on the equator, which are basically related to the Laplacian eigenfunctions and so on. And roughly speaking, that what happens if you fuse 2 operators from the lower hemisphere, like OM and ON, you only get operators on the lower hemisphere, which is like holomorphic fused with holomorphic, only give you holomorphic guys, and that comes from the representation theory. And in the same way, the anti-holomorphic fused with anti-holomorphic gives you the anti-holomorphic guys. And when you fuse the holomorphic with the anti-holomorphic, you get something on the equator, and that gives you the Laplacian eigenfunctions and so on. So next, as you can imagine, our strategy would be to construct this operator, a 4-point correlator, where we have 2 holomorphic guys with scaling dimension n and n, and 2 anti-holomorphic guys with scaling dimension n and n. And the idea is that in the S channel, when you fuse holomorphic with holomorphic, you only get holomorphic guys. And in the T channel, when you fuse holomorphic with the anti-holomorphic, you get the Laplacian eigenfunctions and so on. And so basically here I have written down the S channel expansion and the T channel expansion. And as usual, you can take the 4-point function, write down a prefactor and the function of cross ratio. And then you can take this G of Z and expand in the S channel expansion. And these are the S channel blocks, which encapsulates all the information about the holomorphic forms. So in some sense, once you are given a surface gamma, you know what kind of holomorphic differentials appear on that surface with what multiplicity. So in some sense, you have the full control on the S channel because you know what kind of things appear and with which multiplicity. And in principle, you can also compute these OP coefficients, but we would not need those. And on the T channel, again, you can write down some blocks which are labeled by this delta K, which is related to the Laplacian eigenvalues. So roughly the idea is, using the S channel expansion, you impose S equals T and you put constraint on the possible delta K that can appear on the T channel. And in the S channel, you know everything because the sum starts from 2n and it picks up every even integers. But on the T channel, to begin with, you don't know what kind of delta K appears because that's related to a surface, and the goal is to put bounds on this delta K's. And this slide more or less tells you what's the similarity with the actual CFT. In the actual CFT, you also do a similar kind of trick. The only other difference from the actual CFT is that here z equals 0 is a regular point. So in principle, you can take 2 holomorphic operators and put it on top of each other. But in the actual CFT, you cannot do that. There is OP singularity. But here, the operators are nice. There is no OP singularity in the S channel. And that means you can take this crossing equation and expand around z equals 0 and feed it into SDPP and put bootstrap constraints.
Nice.
Yeah.
How far does this analogy with CFT go? Z was some coordinate when you defined coherent state operator.
Yes, so Z is like the space-time symmetry, the emergent one-dimensional.
Is there some analog of, like, I mean, you said Z is on a sphere. Is there some analog of like torus?
So when I said sphere, I basically mean, so you can think of a 1D CFT. There is a Z variable and you can complexify that Z variable and define it on the full sphere. And that's the sphere I drew. So you can do all the things that you can do with a 1D CFT, for example, in this case. And in general, the story is that if you deal with a D-dimensional hyperbolic surface, there will always be a D minus 1-dimensional emergent, this kind of variables. And you can define operators and blocks and so on. Yeah. Okay, how much time do I have?
10 minutes?
Okay, I think, yeah, I'm good. So, next, let's see how we can. So next we will go into a little bit details of how we put the bounds. So first we start with this 4-point correlator, as I was saying, ON bar. And this n is the scaling dimension. And I told you that this holomorphic and the anti-holomorphic operators are related to the holomorphic differential and anti-holomorphic differentials. And their multiplicity is, like given a surface, their multiplicity is known by the Riemann-Roch theorem. So once I tell you this signature of gamma, which is G and this bunch of numbers, I know how many of them appears. And then the idea is we can get a bound using this single correlator as long as this multiplicity is greater than 0. So if you take a surface, you make sure that there is some n for that ln is greater than 0. You set up this bootstrap problem, you get a bound, and that bound is applicable for the surface. And it turns out we get the strongest bound by applying it to the minimum n such that ln is greater than 0. And then we can tabulate all our bounds using this parameter, which we do next. And it also turns out from the Riemann-Roch theorem that this minimum n can only be these 5 numbers, 1, 2, 3, 4, 6. So that means all the surface must have at least n minimum equals 6. And then you can put a bound using these crossings. So you can ignore these tables for now and these 2 columns for now. So here, these are our bounds coming from the bootstrap. And then there we can also identify the surfaces which almost saturate this bound. For example, there is a surface with genus 0 with orbifold ordering 2, 3, 7, and you can see the bound is 40. The actual value is 44.8835, and our bound is 44.8883537. For genus for n minimum equals 4, the almost saturating surface is 245. Here we have a little bit of gap. The actual thing is 28. We have 30. We do not know why there is a gap, but it turns out to be. For n minimum equals 3, there is a 334. You can see this is 23.07. Here also 23.07. And then here also you can see this, there's 15.79, 15.79, 18.47, and 8.46. In all cases, except for this case, in all cases the bounds are very nearly saturated. And once you have done the single correlator bootstrap, you can do the next best thing you can do, which is the mixed correlator bootstrap. So you can start setting up, thinking about multiple correlators in the one game, and then you can ask this question that what if I have a surface where n minimum is 3, you can ask what is the next holomorphic differential that appear on the surface, which you denote by n prime. And then you can ask if my first guy is 3 and the second guy is 4, what is the bound? And it turns out the bound is 12.2906. And then also you can ask what is the largest known, which is 11.1982. So you can also put some bounds like this using this kind of 3, 4, 3, 5, and so on. And using these tables, you can prove some cute theorems. For example, you can prove the following results. For example, if someone comes and tells you the first eigenvalue is greater than 30.35432, you can immediately tell him or her the orbifold has to be 0237 just by reading those tables. So this is in the spirit of carving out the space of all orbifolds. Basically, using these tables in a clever way, you can basically put some bounds, and using those you can say that if something is greater than something, then the surface has to be this. There is no other option. So basically, you are pinpointing the surfaces. And for higher genus, you can take this strategy and you realize that the dimension 1 guy, the holomorphic differential of weight 1, on a genus G surface, they always appear as G times, so the multiplicity is G. So to put a bound on a genus G surface, basically you set up a mixed correlator problem where each of the operators carries some label A, B, C, D, and all these labels run from 1 to G. So this is a bigger bootstrap problem. And once you run this bootstrap problem for some particular number of G, you get a bound for that genus G surface. So here is our table. You can see we have done up till genus 20, and then also you can put a bound on genus infinity by taking some limits. And these are the Yang-Yao bounds, and these are some improvements of Yang-Yao bounds from the math literature. And these are some bounds specific for the hyperbolic surface by some different methods. In all cases, you can see that our bound, except for genus 4, which you do not understand why, except for genus 4 in all our cases, our bounds are better than Yang-Yao or this improved Yang-Yao or even this bound by the other method. And in genus infinity, somehow we improve over Yang-Yao and this bound by these two persons. But this other method gives a bound 0.25, which you could not beat. In fact, there's a recent paper in the math literature which shows that this 0.25 is an optimal bound. So one cannot do better than 0.25 in genus infinity. And we suspect that the reason why our bounds become weaker and weaker as we go high up, because we are like using a finite set of equations, and probably you need more and more equations as you go higher and higher up in genus. But for low enough values, in all our case, our bounds are way better than the all known values in the literature, except for genus 4. And somehow the interesting fact is from genus 4, still the best known bound is Yang-Yao bound from 1980. So for over the last 40 years, nobody has improved it.
And genus 6.
Oh yeah, and also for genus 6. Yeah, I was looking for that. For genus 4 and genus 6, those two are the anomalous case. Somehow the 1.6 and this 2 is still the best known bound since 1980.
The infinite case is rigorous, or you had some extrapolation?
Which one?
The infinite genus.
Is rigorous, yeah. There is no extrapolation.
I see.
So you take the crossing equation. So the way you make it rigorous, you take the crossing, you get a polynomial from the SDVP, the extremal functional,
Yeah.
And there can be floating point errors, but then you can rationalize all the coefficients, and then basically you can do rational arithmetic and explicitly show that your functional is positive and satisfies all the properties of bootstrap, and that's how we make them rigorous.
Can you do this with a fixed level of exchange operators? Like it's
Yeah. So you use some setup. So there is no truncation, but you only use finite set of equations.
You said, and your error goes like 1 over some power of this set, this size or something like that.
1 over what?
I mean, so your error, like how you're converging.
So it turns out that like initially in the beginning, most of the things it looks like exponentially converging. But at some point it stops exponentially converging and becomes polynomial. But we do not really understand those details.
I see. And you were saying that the coefficient of this polynomial depends on the genus in some way, which is why the infinite case.
Yeah, exactly. Yeah, but those, I guess we do not really understand those details very well. But the bounds that we wrote down here, they are completely rigorous. So one more point, that when the bound is very good, we can actually take the extremal functional from the SDVV and plot it like this. And you will see that the first 0 is 44.8835, that's a rigorous bound. But then there are dips on this function when the dips appears on these values. And these dips nicely approximates the higher eigenvalues for this 0, 2, 3, 7 triangle. So you can see you can numerically solve the Laplacian eigenvalues on this surface, and you get these numbers 44, 142, and so on. And these numbers matches pretty well with these other dips. So in some sense that like when the bound is very good, you can actually hope to get the extremal functional and approximate the higher eigenvalues very well. Similar extremal functionals also appear in the context of sphere packing and also in many other cases. And there lies the hope that maybe one can bootstrap the chaotic spectrum of some non-arithmetic surface and plot something like this, where the dips will be have some chaotic spectrum. So finally, we have some future directions, and of course one can do mixed correlated bootstrap to produce sharper bounds at large genus, because the large genus bounds are weak. Then one can consider SL2R, which has additional irreps. For example, like we have not considered spin half representations in our story, so you can add those things in the game. We are right now exploring the higher dimensional orbifolds, especially the 3D ones, where the thing will be played by SO1, 3. Then you can consider non-orientable surface, where the relevant group would be PSL2R, semi-direct product with Z2. One can explore much more with the connection of the D-seater bootstrap. Then there are non-compact hyperbolic orbifolds. One can perhaps put bounds on the cost forms. And then actually finding a bound which is saturated by some chaotic non-arithmetic surface, like whether we can actually harness the chaos by using the same bootstrap techniques. So with this, I will end with this slide, where I have plotted the level statistics of those two triangles. As you can guess, that this one is the chaotic 0, 3, 4, 5, and this one is the Poissonian 0, 3, 4, 6. And the hope is somehow you set up a bootstrap problem which would land up with this surface, and you can actually see from the dips that there are some chaotic spectra and so on. It would be very nice, because it would be an example where you are doing the actual bootstrap and the extremal functionals are giving you something chaotic. Thank you. Questions?
Is plot from Bootstrap or from numerical plot?
No, this is just from numerically solving it. Yeah, it would be a dream to reproduce this plot from the bootstrap.
So from that function you said, from the double.
Yeah. Yeah, for these triangles, you can easily set up solve the Laplacian equation, like create a maze, and there is a program free FEM.
Does the genus appear as a parameter, just basically a parameter in your bootstrap, or did you have to, for every genus, you have to set up a different?
Yeah, basically you are setting up a mixed, so the external guys appears as O1A, O2A, and those external guys has a vector space dimension G. So for every genus, you have to set up a problem.
Has someone tried doing this for the actual bootstrap, like 3D-izing using functional?
I don't know, in 3D, I guess, no, I think probably to see the chaotic spectrum in 3D-izing, you have to go high up. I don't know whether anyone has gone that high up.
Because here you just got the functional by being very precise about the first eigenvalue.
Yeah.
The best bootstrap results don't really get you. You get maybe the first 100 operators, but the operators are of different spins, so you get the first 5 scalars or something. Nowhere near enough to be able to see this.
And here we're not talking about rigorous bounds, right? You're just saying some kind of estimates based
Yeah,
on
yeah. Right.
If there are no more questions, let's thank the speaker again.
I have a list of the first 100.